Next Monday is okay. Next Tuesday is a holiday. Next Tuesday and Wednesdays are holidays, especially for exchange students. Those next Tuesday and Wednesday are holidays. Also, there's a practice that the Chinese New Year Eve, a lot of office close earlier, work half day. University, for administration, I think it's half day. But for classes, do we have half day for classes? We do. Okay, officially it's supposed to be no class after 2 o'clock next Monday, the Chinese New Year Eve. It's a very important day for Chinese. So we have to prepare reunion dinner and then eat dinner. So it happens that we have our class, our lecture from 2 to 4 next Monday. So we follow the instructions, so no class. But does not mean no lecture, all right? I don't want to make up that, but I'm going to upload a video which is taken from the webcast last semester, all right? So in other words, there's something like the nonsense that I'm talking about now, all right, may not apply. Okay, so it's in the record in the webcast last semester. So you can you watch and then remember, like if the announcement saying that the midterm tests be held in August last year, it does not apply to you. All right, so I'm going to upload the once I got ready, I will upload the webcast that cover the topics that we are supposed to cover in the next lecture Monday. And maybe I also check with the other group, maybe also Tuesday topics as well. Before I come here, I just upload chapter 2 lecture notes on random variables in both IVLE as well as Luminous. All right. So that's the lectures. As for tutorials, next Tuesday and Wednesday are holidays. So those who have tutorials on Tuesday and Tuesday and Monday after 2. So I believe it's group 4, the one that is group 4, 5, 6, 7, 8. That means those 4 Monday after 2 and on Tuesday. So what to do? Okay, so we offer you to go for makeup to the other to attend other tutorial groups for makeup for next week. All right. Okay, so that's the second thing about tutorial. The third thing is about the midterm test. Unfortunately, we have a big group, not this one, but 3 groups. So a lot of problems. So it seems that we're still working very hard on the time. But most likely it's March 9th, Saturday. We still want to have it on Saturday. But we may have to switch back to the morning because I was told that one of the time clash seems no more exist. So, okay, it's not finalized. So I'm sorry, it's very confusing. Me too are very confused. But it will be either, okay, it's likely to be in the morning, but maybe still chance to have it in the afternoon. And I understand that the 9th of March is open day for the university. I'm sorry about that. We can't help. All right. So we'll still have this this test on March 9th. All right. Wait until you got the announcement. So it's not finalized yet. So you leave the Saturday open and likely to be in the morning. We don't know. There are so many constraints about this time, the timing. All right, so bear in mind it may be in the morning. All right, so that's the 3 things that I have to let you know. Webcast shouldn't have any problem now, right? You can access the webcast in the Luminous. Okay, so let's start our lectures. . Okay, so here's where we stopped yesterday. So now we continue, and okay, so it's still just a few more examples about this Bayes theorem. Okay, this one you can read it yourself, but I want to talk about this example 6 and example 7 as well. All right, so so we have these components shipped to us, all right, in a batch of 10. So each batch has 10 components, all right, and 50% of the batches have no defective, while 30% have one defective. In other words, the 50% of the batches, out of these 10 components, none of them are defective. The other 30% are batches with one defective component, and 20% with two defective components. All right. So, what's the percentage of batches have 3 defective components? We are not given, but we can tell because these numbers add up to 100%. That means 1. What does it mean? It means that it already covers all the possible batches. All right. So, in other words, for any one batch, is either one defective, 2 defective components, or no defective components. It cannot be other number of defectives, although we have 10 components in the batch. So now we take 2 items from the select batch and test. So what's the chance that the probabilities associated with 0, 1, 2 defective components being in the batch if neither test component is defective. So now we take the 2 items or 2 components out and test it, have some information about it. So both of them are non-defective. So now we asked, what is the chance that the batch chosen belongs to the group with no defective, or 1 defective, or 2 defectives? All right. Now, without this information, the probability of 0 defective is 50%, 1 defective is 30%, and 2 defective is 20%. So now we have this additional information. So what are these probabilities? So it's very important that you have to identify your events in this case. So now I let AI, all right, represent the batch with I defectives. All right. So A0 means that that is the batch with no defective items. A1 means 1 defective item, and so on. While DI, it means that there are I defectives in the sample, a sample of 2 taken from the batch of two components. All right. So it seems like we cover about the batch. So use A to denote the batch and identify A0, A1, A2 as the type of batch. And also we take a sample of 2. We identify what happened to this sample, whether it's 0 defective, 1 defective, or 2 defectives. So these are the information. So now we try to link up, once we define the events, we try to link up the events with a probability. So what is probability of A, not A1, A2? So these are the corresponding probabilities. Then how about probability of D's? Wow, that is harder. Why? Because think of it, if you take a sample of 2, how many defectives are there? Depends on which type of batch that you get. So in other words, we try to work this out. Probability, let's say, start with something more concrete. D0 given A0, for example. All right? Then we have to work out probability of D0 given A1, probability of D0 given A2, Do we have to work out this one? There's no such thing, huh? Because we don't have A3. We don't have a batch with 3 defectives. All right? So basically, we try to work out all this. All right? Why we have to do that? Because once we identify the batch that you chose, then we can answer the question, what's the probability of 0 defectives? So this one, we have to go back to use our combinatorics arguments. So you think of it, if you take a batch, if there are 2, you select 2 out of this batch, out of 10 items, so the number of ways to select is choose 2 out of 10. Choose 2 out of 10, which is 10 factorial divided by 8 factorial, 2 factorial. So it's 45. All right? Now, if we know that that batch is a batch with 0 defectives, all right, then the number of ways that you will get, all right, 2 non-defective items out of the batch, out of the A0 type. What does it mean? It means that I have these 10 items, I divide into 2 groups. One group are the non-defective and the defective. So for A0 type of batch, 10 of them are non-defective, and 0 of them are defective. And out of this non-defective, you choose 2. Then the defective one, you choose 0. So this basically is just 1. All right, so it's 10, I choose 2, over 10 choose 1. So what does it mean? It means that if we pick up the batch of no defective type, then sure, you will get, if you select 2 items, both are non-defective. You won't see any defective items. So similar arguments, all right? How about D0 given A1? So this time, A1, we have, A1 means that you have 1 defective and 9 non-defective. You have to choose 2 out of those 9 defective and 0 out of the 1 defective. You don't choose the defective one. How many ways to do it? And you multiply them. Now, why multiply them? Because the number of ways that you choose 0 items from the 1 defective items, you will have so many of ways to select 2 non-defective out of 9 non-defective items. So similarly, for A2, so it will be 8 and 2. Because there are 2 defective, you choose 0, and 8, you choose 2. So these are the corresponding probabilities of getting D0, given the knowledge of AI. Then the next question is, okay, we apply the law of total probability. We got P probability of D0. That means, okay, what's the chance that you got a 0 defectives out of a sample with 0 defectives? That means D0. All right, so it's equal to, first select the item, a batch with no defective, the chance of no defectives out of the sample, and similarly you do the same thing. So now altogether you got 0.86, which means that you select a batch, we don't know what it is, and then select a sample of 2 from this batch. The chance that you have non-defective, both are non-defective, the chance is 0.86. All right? So you just have to remember, you select a sample, and you ask what's the chance that both the 2 items are non-defective. It depends on which batch. So you have to consider for each batch. Calculate the probability, but also you have to multiply the chance of selecting that batch. Okay? So now we apply the Bayes theorem. So if we see no defectives, so what is the chance that it is from a batch with no defectives? That means what is the chance that it is A0? Okay? So you see the idea of Bayes theorem is like this. You pick a batch first, and then you select the items, select the sample. So now you know the result of the sample, and then you go back to check what's the chance that it is from A0. All right, so we apply the Bayes theorem, so it turned out to be 0.5784. Right, this one basically is probability of A0 given, probability of A0 intersect D0. All right. Okay, so it's 0.5784. So what does that mean? Now, without the knowledge, without looking at the sample, the chance of A0 is 0.5, half, 50%. But once you draw a sample and find out that both of them are non-defective, then the chance increases to 0.58. 0.58. All right, so we can work out similarly for the other chance. So for A1, so decrease from 30% to 28%. So for A2, so it reduced to, from 20% reduced to 14%. Right. So this information tells you that it's likely from a batch with with no defectives. All right. So this is the use of the base. Okay. This is an interesting example. Example 7 is called Monty Hall problem. So it's a TV show, maybe quite some years ago. So it's a very simple game, TV show. So there are 3 doors, all right? And then behind the 3 doors, one of the doors have a car. The other 2 have something useless. For a TV show, there are goats. There's some that goes, all right? Maybe it's still not bad. Right? We can bring home and do whatever you like. Treat as a pet or treat as food, all right? Okay, so you open a door. Not open. You choose a door. You cannot open. You choose a door, all right? And then the TV host will open a door for you. So he will not open a door with a car behind it. Then. All right. So you open a door. You choose one door. There's still 2 doors, and 2 unchosen doors. So they will open one for you. Sure, that one will be a goat, not a car. Then here is the most important part. I ask you, would you like to switch your choice? So now the question that we ask is, do we want to switch? Will you switch? How many will you? Okay. You think about it. How many of you will switch your choice after you see the host open the door that show that no car behind it? Or you will switch? How about others? You stick to your original choice? If you have previewed the lecture notes, you know the answer, right? Or if you really think that you should switch, then yes, you're lucky, you got the correct answer. But why? Okay, so here's the explanation. A very simple example to illustrate the conditional probability. What is the conditional probability? Because now we have additional information. Okay, so I already explained the problem, so now we look at it. Okay, so let's look at 2 strategies. And to decide which to choose, we pick the strategy that have a higher chance to win the car. All right, so let's say we don't switch. All right, so what is the probability of winning? Now, here I try to explain to you. Now, if I choose a door, because no information, so they have 3 doors, so I choose one, so the chance that I will win will be 1/3. Correct or not? You know no information, so anyone can be equally likely. So it's 1/3 chance. All right? Now, so if the door that you choose is a winning door, then your chance is 1/3. All right? But there's 2/3 chance that you will get a non-winning door. Right? In other words, okay, car, goat. So if I choose this one, all right, with 1/3 probability that I will choose this one, all right? So if I stick to this one, okay, I don't care what they open this one, I still stick to this one. So the probability of winning, all right, is still 1/3. That is 1/3 after you don't switch. So the chance that you win will be conditioned on what you choose is 1. But if I choose any of the gold, the door with gold, all right, then okay, so 2/3. So we then, okay. So if we don't switch because you still have it. So once it opens, you lose. So it's 0. Okay, so you don't, remember, you choose, this is the chance that you choose the door with the car. And this is the chance that given that you choose the door with the car and then you don't switch, all right? No switch. So if no switch, you will win. So that's why it's 1. This was 1/3. Plus the chance that you choose the door with gold. And then, with probably a gold, and then you choose not to switch. No switch. All right? Then this is sure is 0. All right? You stick to the door with a gold, so it's lost. So that's the conditional probability. You can either, so if I draw it, it will be like this. For this strategy, so a car and gold. This is 1/3, this is 2/3. Then you win, you lose. This is 1 because you don't change your strategy, and 0. This one, the chance of winning is 0. So that is the diagram to illustrate your strategy. So that at the end, the winning strategy is only 1/3 if you stick to your strategy. So at this point now, I can conclude that either you switch or you don't switch. So if you stick to this non-switch strategy, the chance is 1/3. So of course, if you switch, the chance of winning is 2/3. Am I right? Do you accept this argument? There are only 2 choices. Stick to your choice or switch. So if stick to the choice, you have 1/3 probability of winning. So the other strategy will have a 2/3 of chance winning. Right? Simple. But I want to show you through the conditional probability argument. So switch strategy. So now, so this is the probability that you choose the okay, I choose a door with a car initially. All right? Then with the car there, I switch. This time I switch. All right? So the chance of getting a car, you choose a door with a car behind, but after you are asked to decide whether you want to switch, you switch. So now the probability of winning, it becomes 0. On the other hand, if you choose a goat and then you switch, all right? So what's the chance that if you switch, what's the chance that you win? 100%. Why? Because, think of it, this is my initial one. If I choose, the one that I choose is a goat, all right? Then the host must open this door. Open this door, so I know that, okay. Open a door, it opened the door, so it's goat. So this one must be car. So if I switch, I will win the car, right? Okay, because think of it, if the story, okay, the story will be different. If the host will not open the door with the goat to show you, all right? It just toss a coin and then decide whether it's open or not. Things like that, then will make it more complicated. But once you open, you know that there are only 2 doors left behind, and then we switch. If your original choice is a goat, when you switch, you will get the car. Then you ask, okay, if your original choice is car, yes, in that case, when you switch, you will lose. You got 0 probability of winning. That's the beauty about conditional probability. So it's 1/3 times 0, 2/3 times 1. So it's 2/3 chance. So my point, I want you to be aware of that. A simple game illustrates the idea of conditional probability You have to work hard on to calculate all these probabilities. Also, I also demonstrate if I work on one strategy, the other is just a complement. So if I work out probability of stick strategy, your chance of winning is 1/3. So the probability of switch your strategy, work on the switching strategy, your chance of winning will be 2/3. All right. So unfortunately, everyone knows this trick. So I don't know whether they still have this kind of games, but yes, definitely you have to switch. All right. So these are the YouTube video that show how this works. So if you don't see don't have chance to watch the game, then now you can watch it through YouTube. Okay, independent events. So independent event is very, very, very important, because once we have this independence properties, then it makes our life much easier. Okay, so let's consider an example of toss a die twice. Okay, we define A is the first die or first toss, is an even number. B is the second toss, is a 5 or 6. All right? So we try to work out the probability of these three events, A, B, and A intercept B. All right? So this one, the possible outcome is 36, and the first toss is an even number. How many out of these 36 possible equally likely outcomes that will give you the first one as even numbers? You can think of it like this. The outcome represented by I and J. So there's 6 choices here and 6 choices here. That's why altogether you have 36 outcomes that are equally likely. So in order to get an even number as the first toss, that means you are looking at 2 star, 4, and 6. So this one has 6 of them. This one also 6, this one also 6. So altogether there are 18 of them. So it's half. So this one, 5 or 6. So that means it is asterisk 5 and asterisk 6. So 6 here, 6 here, so altogether 12, 36. So it is 1/3. All right? Then how about the intersection? The intersection means that the first one is even and the second one must be 5 or 6. So it will be 2, 5, 2, 6, 4, 5, 4, 6, 6, 5, and 6, 6. So altogether there are 6 of them out of 36. So it's 1, 6. All right? So these are the probabilities. Why we have to work on these probabilities? So we want to show you that the conditional probability of A given B. That means if I tell you that the second toss is a 5 or 6, what's the chance that the first toss is an even number? So followed from the definition, it turns out to be 1/2. And this happens to be the same as probability of A that we just shown. So in other words, the conditional probability of A given B is the same as the unconditional probability of A. So what does it mean? It means that, okay, even if you know what's the outcome of the event, you know event B has occurred, it will not give you additional information or will not make you change the probability of the event A occurs. So that means A and B, these two events has not linked. We call it independent. All right, A and B are independent. That means the knowledge of one of them will not change the probability of, will not lead to a different probability of another event. So in other words, the conditional probability and the unconditional probabilities are the same. All right. In fact, the other round is also true. The probability of B given A is also the same as probability of B. So this is one of the properties or interpretation of independent events. The probability will remain the same for conditional probability and the marginal probabilities. All right. So this is the definition. Two events are independent if and only if probability of the intersection equal to the product of the two probabilities. All right. Now, I don't know, you know what if and only if means? What it means is that if you have two independent events, then this is true. Or if you have this it being true, then these two events are independent. All right? So these two are equivalent. When we use the word, the phrase if and only if, means that these two things are equivalent. So A and B are independent is the same as saying that probability of A intercept B equal to probability of A times probability of B. Then, so if they're not independent, yeah, then it's called dependent. All right? Okay, so if A is independent of B, then B is independent of A, because it's the same thing. All right? Now, here are some properties of independent events. Some are very important. So here I say that, okay, if we have two events such that the probability of A is bigger than 0, probability of B is bigger than 0, then if A, B are independent, then this must be true. So in other words, to define independent events, you either you have this one, which is our definition, but in fact, it also have this property and this properties. So one of these three, this one, or this one, one of these three statements, one of them, in fact, they're all equivalent. All right? But if you can check one of them holds, then we say that A and B are independent. So this is a little bit confusing. I understand some of you will think that independent event and mutually exclusive event are the same. In fact, there are two different concepts, two different properties. They are not equivalent, and one does not imply the other, one does not reject the other. Okay, so they're different. So here I say that, okay, we have two independent events, then they cannot be mutually exclusive. And it's quite obvious. You can see that for independent event to make sense, this probability, in fact I have here, all right? So you have this holds for independent events. But because this one is bigger than 0, probability of B is bigger than 0, so the product is still bigger than 0, which means that this one does not equal to 0. This one does not equal to 0. It's bigger than 0. Bigger than 0 means that it does not equal to 0. So therefore, A and B cannot be mutually exclusive. All right? So, because probability A intercept B is not equal to 0, therefore the intersection of A and B cannot be empty set. Okay, another properties, this one, the other way around. If they're mutually exclusive, then they cannot be independent. They cannot be independent. Why? Because if it means mutually exclusive, that means this equal to 0. All right? But the product of A and product of B, the product of probability A and probability B will be bigger than 0. Therefore, these two cannot be the same. One is equal to 0, while the other is bigger than 0, so they cannot be the same. So therefore, A and B are not independent. All right? Now, okay. So this is a little bit funny. So I say that any event is considered independent of the sample space as well as independent of the empty set. All right? So you can interpret like that. Knowing it is from the sample space, no additional information given to you. So that's why it's considered independent to the sample space. Knowing that nothing happens, empty set. So again, it won't tell you any additional information about the event. But you can prove it mathematically. So for any event A intersect S, because S is the sample space. Remember what is sample space? Sample space is the set consists of all the outcomes. So A intersect S equal to A, and A intersect empty set is equal to empty set. So therefore, probability of A intersect S is equal to probability of A. This follows from these properties, all right? Because A is a subset of A intersect. Sorry, A intersect S is a subset, it's equal to A. But on the other hand, wow, why this is equal? Because I just want them to be equal. Why I can write probability A equal probability A times probability S? Because probability of S is disguised as probability S, but basically it's 1. I multiply 1. But I don't write 1, I write probability of S. So intersection probability equal to the product of the two probabilities, so it fits to the definition of independence events. So A and S are independent. All right? So that's mathematically proved, the proof of it. You can also interpret in the following way. You think of it, A and S, two events are independent. That means knowing S, all right, knowing S, will you change the probability of A? No, because probability of S is just saying that anything can happen because it cover all the possible outcomes. All right, knowing S occur does not help you to. On the other hand, think of it. If you know A has occurred, like I asked you, I toss a coin, I toss a die. Okay, the outcome is 1. What's the probability of 1, 2, 3, 4, 5, 6? It's still 1. It doesn't matter what your outcome of your toss. It must be one of this 1, 2, 3, 4, 5, 6. Right? So knowing A will not change your probability of S. Knowing S will not change your probability of A. So that's why they're independent. So similarly, I can also prove that S and intercept is. So it's like this. This one is equal, the intersection is equal to empty set, means this is 0. So 0 can multiply to any number, is still 0. So I add probability of A. So it doesn't matter what probability of A is. So again, it fits to the definition of independent events. All right? So S is independent to any event. Empty set is also independent of any event. If you have two events, A is a subset of B, then they are dependent unless B equal to S. Right? So work on the definition. If A is a subset of B, so A intercept B is equal to A. Therefore, probability of A intercept B is equal to probability of A, which does not equal to probability of A times probability of B. This is not equal unless probability of B equal to 1. In that case, B is S. B is the sample space. All right? You see, that's how mathematicians do things. In general, if A is a subset of B, then these two are dependent events, except one scenario. B is the sample space. B is everything. Then in that case, then A and B are independent. Now, please remember this. Independent events cannot be demonstrated using the Venn diagram. Okay, you can show mutually exclusive events, you can check intersection, check union, but you cannot draw a Venn diagram to illustrate A and B are independent. All right, so because you cannot draw a diagram, so it's likely that you better don't trust your intuition. All right, yes, you may have a good intuition and most of the time you're right, but be careful. All right. So we already showed that mutually exclusive events are dependent events. Now here I try. These are not proof. But I try to illustrate. I try to pick events. All right. So here I try to show that mutually exclusive events, but they're not independent. All right. So now all these examples are based on very, very simple scenario. Toss a die. So A is getting odd numbers. D is getting even numbers. All right. So therefore, A and D are mutually exclusive events. All right, obvious, right? Now, what is probability A, probability D, and probability A intersect D? So immediately you can see that A and D are not independent because the intersection is 0, all right? And while the product of A, probability A and probability D is not 0, so they are not independent. All right. So I can also show that still not independent, but at the same time, they're not mutually exclusive. Just now I showed you examples that they're mutually exclusive events, but they are independent. They're dependent. So now I also show that, going to show you, they are dependent events, these two, but they are not mutually exclusive. You can see that they are not mutually exclusive because there are some common point, 1 and 3. So now you can see that probability A intercept B is outcome 1 and 3, so it's not mutually exclusive. Probability A is 1/2, probability B is 1/2, probability of A intercept B is 1/3, 2 out of 6, so it's 1/3. So the product of 1/2 and 1/2 does not equal to 1/3. So therefore, A and B not mutually exclusive and also not independent. So in other words, this independence and mutually exclusive, these two, all right, are not related. You cannot have one implies the others. Now, I also showed you that non-mutually exclusive event but independent. So I find two events that are independent but they're not mutually exclusive. Still have this A, and now I have a C, which is a event which is number less or equal to 4. So A intersect C is 1, 3. So they're not mutually exclusive because this is not empty set. And on the other hand, the product of the two probabilities turn out to be the same as the probabilities of intersection. So they are independent. All right? All right. Okay, so my point is don't mix up the mutually exclusive events and independent events. All right? Okay. So, but you notice that these 4 combinations are independent or not on one hand, and mutually exclusive or not. I just give you 3 examples to illustrate. I don't have example for the 4th one. The 4th statement is true. That means, think of it, what was the 4th statement? I showed you the first example. What's my first example? Mutually exclusive but dependent. The second one, not mutually exclusive, dependent. The third example I showed you, not mutually exclusive but independent. All right? So what's the 4th one? Mutually exclusive and dependent. So that one okay, that one is, if I'm not wrong, it's true, right? So I just give you 3 examples, 3 scenarios to show the relationship between exclusive or non-exclusive with the independent or not independent events. Okay, example 1. So obviously, if these two are unrelated persons, okay, each guy has a chance of 0.1 make a mistake of 0.1 chance of making a mistake in doing something. In this case, it's filing the test return. All right. What's the chance that 2 totally unrelated persons each make a mistake? All right. So unrelated person is very important. That means they're independent. So So the probability will be 0.1 times 0.1. So I let mi be the person I here. I consider only two persons. So I from 1 to 2. So I'm m1, the first person make a mistake. The second, m2 represent the event that the second person make a mistake. And these two are independent. How do I know it's independent? We assume that unrelated person means that what they do will not be linked or related. So most likely they make mistakes independently. All right? So this one, two totally unrelated person, each make a mistake, which means that we're looking at this m1 intersect m2. So the probability is 0.1 square. Okay, so here is a theorem which is also very useful. It's saying that if we have two events that are independent, then A and B complement, A complement and B, and A complement and B complement, all this will be considered, that A and B complement are independent. A complement and B are independent, and A complement and B complement are independent. All right, so this is very useful. So once you know that two events are independent events, then their complements will also independent. All right. So let's say, all right, we have this gentleman will alive in 20 years' time is 70%. Jack, maybe younger, so still alive 20 years later is 0.9. So now we asked, what's the chance that neither will alive in 20 years? Now you must understand the question. So here he asked, okay, none of them will still alive in 20 years. So what does it mean? It means that, okay, what notation do I use? A and B. So we let A be the event that Tom lives more than 20 years. B is Jack lives more than 20 years. All right? And we assume that they're independent. Yeah. Okay. Unfortunately, the question did not say that these two are independent, but we have to make that assumption. Otherwise, you need more information. All right. So whether Jack still alive in 20 years and Tom still alive in 20 years, they are independent. We make that assumption. But if the two are, let's say, brothers, then may be different. If they're siblings, if they're brothers, then they may have the family history of similar type of illness, so that may change the things. All right, but here we assume that they're independent. But my point is, I have to translate in terms of A and B to address this event. Neither will be alive. That means A will die within 20 years and B will die in 20 years at the same time. Okay, so that's what it means. Neither will be alive. So therefore, it's A complement, that means it died within 20 years. Tom died in 20, and B, Jack died in 20 years. So we calculate this. Alternatively, you can interpret as this way. Tom still alive in 20 years. Jack still alive in 20 years. One of them still alive in 20 years. Either one or both of them still alive. And then take the complement. All right? Let me repeat again. So A union B means that Tom will alive 20 years. Jack alive 20 years. Or both alive in 20 years. So the complement of it means that both of them will not alive in 20 years. So this is the same. If you remember, we have this identity. All right. So you must, if you know this identity, will make it easier. Okay, so it turns out that it's 1 minus 0.7 times 1 minus 0.9. So the answer is 0.03. So in 20 years, you won't see both of them is only 3%. So at least you see one of them or both of them with a probability equal 0.97. And independent events. Now, independent events is more complicated. So we have 3 events. All right? Oh, okay. We have n events. Okay, let's look at pairwise independent. Once you see this word, it means that you may have more complicated. Pairwise means that you just take 2. So out of n events, you take 2 of them, any 2 of them, and they're independent. So in that case, we say that they are pairwise independent. All right? Any 2 of them, the intersection with probability equal to the product of individual probabilities. That's pairwise independent. This is the one that we need. Mutually independent. That means not just 2. You pick any of them, any number of them, they are all independent. So that is the meaning by mutually independent. So take any subsets, all right, of AI1 up to AIK. So in other words, you can take any 2 of them so that this is true. So if K equal to 2, then you just take 2 of them, any 2 of them, the probability of the intersection of these 2 is equal to the product of the 2 probabilities. You can take 3. So AI1, AI2, and AI3. Any 3. Then the probability of the intersection of these 3 is equal to the product of the 3 marginal probabilities. You have to check every possible combination. Wow, so it's a lot of work. All right? So that is mutually independent events. So I give you, all right, this is the interpretation of mutually independent event. So if you have A1 up to AN, then any 2 are independent, the multiplication rule holds, any 3 of them are also holds, and so on, and until the last one. N of them. The product of the intersection of n of them is equal to the product of the individual probabilities. So if I have 6 events, right? If I want to check whether they are mutually exclusive, how many probability statements that I have to check? So I have to check, take A1, A2. I have to check probability A1 intersect A2 equal to probability A1 times probability A2, right? So for 2, I have to choose 6 out of 2, right? That's the number of checking that I need to do. Then the other one, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. These are the number of probability that you need to check, whether they are mutually exclusive. A lot, right? Only 6 events only. If you have 10, even bigger. All right? Okay. So altogether is 2 to power n minus 1. How to get this one? Very simple. So it basically consider you have n boxes, right? So you consider whether it's including or excluding that particular box, or whether it's empty or not empty. If all are empty, that means none of the events are, all the events are excluded, which is not the case that we want. We want at least 2 of the boxes with something in it. All right? So what we are looking at is you can say n boxes. Okay, you can think of it, you have n boxes. All right? Now you have n cons. So either you can put none of the cons that you put in the n boxes. In that case, that means you choose no event. All right? You can put one into one of these boxes. All right? Then there are only one event, but these are not what we want. So at least we put 2 cons in these boxes. So how many ways that you can put 2, all right? And then how many ways you can put 3 and so on. So it's the same as whether a box, one of these n box, whether it got a con in it or not. Yes or no, right? If it happens that this has something in it, this has something in it, this has something in it, all have a con in it, then it means that you select all the events. How many ways that you have such thing? Only one way. But if you have only n-1 boxes in it, have cons in it, how many ways that you can have? That means which one is empty? It can be the first one is empty, it can be the second one is empty, and so on. So we translate this problem as if you look at from a box point of view, whether you have something in it or not. All right? So the number of possible ways is 2 to the power n to get the arrangement, 2 to the power n. 2 times 2 times 2 times 2, n times. So it's 2 to the power n. But out of so many choices, there are 2 types are not what we want. The first one is every box is empty. That means you choose nothing. So that's not what we want. So -1. How about the n? N is the number of ways that you get only one event. This is, again, is not what we want. We want at least 2 events. That means 2 of the boxes must have something. How many ways that you have 2 boxes in it? So that's why we -1, which is the number of ways that you have all event not chosen. This is the number of ways that you can choose one event. This is not our, we don't need to know those. We only start with 2 to the power. We only need to have at least 2 events being picked up. That means 2 of the boxes have something in it. So mutual independence implies pairwise independence. So this is obvious. Mutually independent is a very, very strong condition, strong statement. All right? Pairwise independence is only a part of it. Okay, you remember, that's what okay? So, in order to have mutual independence, you have all this. You have all this. So pairwise is just this part. Only 2 of them. Any 2 of them. Any 2 events of them are independent. That is pairwise. So therefore, the mutually independence implies pairwise. But pairwise does not imply mutually independent. So here are some examples to illustrate. Before that, if they are mutually independent, then this that means if they are mutually independent, then complements are also independent. So that means if I replace one of them or any of them by their complement, this set of events are still mutually independent. If these are mutually independent, then A1 prime, A2 prime, A3, A4 up to AN. For example, this set of events are also mutually independent. You can replace any of the events by their complement, and the resulting set of events still are mutually independent. Okay. Now, we toss a die 3 times. Okay, the first toss gives an odd number, second toss gives an even number, and the third one gives a value greater than 4. So here are the events, A, B, and C. All right, first toss is an even number. First is A is an event that the first toss is an odd number. B, the second toss is an even number. C, the third toss is a 5 or 6. So what is probability of A? So it's 6 times 6 times 6. While for A, it means that it has to be 2 star star or 3, 4 odd number. So it's 1 star star, 3 star star, or 5 star star. So how many of them here? 36 here, 36 here. Or you see, 6 choose 1, 6 choose 1, and altogether the first one I have 6 choose 3. Okay, sorry. So I choose out of these 3, 1, 3, 5, I choose one of them. So altogether the chance is half. Similarly, probability of B is 1/2. Probability of C, so all will be selected for the first toast and the second toast. The last one, either 5 or 6. So it's 2 out of 6. All right? 2 out of 6. But the number of ways to choose is 2, 5 or 6. I'm sorry, it's a bit confusing. So basically, the way that I present here is to look at the possible way to select. Okay, the outcome, possible outcome is 6 times 6 times 6, 216. While the number of ways that you can have to fit to the description, number of ways is, for example, C, you need to have star star and 5 and star star 6. You need this kind of thing. So star star 5, 36 of them. How to get it is 6 times 6 times 1. Then plus 6 plus times 6 times 1. So instead, we can just say that, okay, the first one we have 6 choice. The second one we have 6 choice. The third one we have 2 choices. So it's 6 times 6 times 2. All right, 6 times 6 times 2. So here the following computation is just to illustrate that they are all pairwise independent. Any 2 chosen from this are independent. All right? So they are pairwise independent. Now the question is whether they are mutually independent. So I have to check this, whether it's equal to probability of A times probability of B times probability of C. So A means the first one is odd. The second one, B means the second toast is even. And C means the last one is 5 or 6. So this is the number of ways. All right? 1 over 12. But I can write 1 over 12 as 1/2 times 1/2 times 1/3, which is the probability of A times probability of B times probability of C, which means that A, B, C are mutually independent. All right? So, now remember, mutually independent, you have to check possible 2, choice of 2, possible choice of 3, possible choice of 4, but we only have 3, so we stop here. So mutually exclusive. A, B, C are mutually exclusive. All right, so A, B, C are mutually exclusive. Yeah. So how about if I define C, that, okay, so now I toast 2 dice, not 3, 2. First one is an even number, second one is an odd number. C is an event that 2 dice shows both odd or even, or both even. So what does it mean? A is equivalent to 2 star, 4 star, and 6 star. B referring to star. Star means 1, 2, 3, 4, 5, 6. 1, star 2, and 3, and star 5. How about C? C means that both, so it will be 1, 1, 3, 3, 5, 5, 2, 2, 4, 4, and 6, 6. So this is C. So immediately you can see that All right, there's something that's interesting here. So we work out the possible A, B, and C. Oh, my mistakes. I'm sorry. Both are odd. So it's more than that. 1, 1, 1, 3, 1, 5. All right. So 3, 1, 3, 3, and 3, 5. 5, 1, 5, 3, and 5, 5. Similarly for this one. I'm sorry about that. All right. So altogether, there should be 18 of them. So the answer is 1/2. Okay, this is a more, you see, I hate to do this kind of, write it explicitly. You should think of it like this. All right? This is the possible choice, possible ways with two dice. Now here, what does that mean? It means that you think of it, the first one, all right? So we assume that we're talking about odd, right? So there are 3 odd numbers. So the first outcome can be 1, 3, or 5. So this is to choose one out of this 1, 3, 5. All right. After that, the second dice can be any one of the 1, 3, 5 again. So that's why it is choose 1 out of 3. So multiply them together. All right. So similarly, this means that the number of ways you choose from 2, 4, 6, and number of ways to choose for the second die is 2, 4, 6. So altogether 1/2. So if you check, A and B are independent. A and C are also independent. How about B and C? B and C is also independent. Wow. So they're pairwise independent for these 3 events. But on the other hand, what is probability of A intercept B intercept C? All right, it is 0. Because it's the first one, A means that the first must be odd. The second one is an even. The second toss is even. So the A and B occur together means that they cannot be the same. The 2 outcomes cannot be the same. A means the first die is an odd. B means the second die is even. So if A and B occur together, that means 1 odd, 1 even. It cannot both be the same type. So it's equal to 0. So on the other hand, probability A times probability B times probability C is equal to 1x. So this is not true. This does not equal to this. So it means that it failed the mutually independent test. So only pairwise independent. All right, so you have to remember when we say independence, so there is pairwise independence for n events, but if you want to say all of them are independent, it's mutually independent, so it implies that any subset of this set of n events are independent. Okay, so let's say we have 3 engines operate independently, and each engine is available when needed is 0.9. So what is the probability that no engine is available when needed? So this is the key word, independent. So you can think of it, all right, A1 or E1, E2, E3, to represent that the engine, the ith engines are available when needed. All right. So no engine is available means that the first one is not available, and at the same time, second one is not available, and the third one is not available, which is the same as saying that, okay, E1 may be available, E2 may be available, or both are available, and E3 may be available, or all 3 may be available. So this means that you have engines available. The complement of it means that none of them are available. And these 2 are equivalent. All right? So it depends on how. So in this case, it may be easier to work with this probability. It's harder to work on this probability. Because to find the probability of E1 union E2 union E3, I don't know whether you still remember this one. This one equal to 1 minus probability E1 union E2 union E3. How to get this probability? I don't know whether you still remember this inclusive exclusion principle. E1 plus probability E2 plus probability E3, and then minus probability of E1 intersect E2 and so on. Quite a number of terms. But if you work on this one, it would be much easier. So because they're independent, so probability I prime is equal to 0.1. So probability of E1 prime intersect E2 prime intersect E3 prime, because they're independent, so it's equal to the product of these three probability. So the answer is 0.01. So the chance of you don't get any engine available when you need it is only 0.01. All right? Okay. Here's another example. Okay. This is a very lousy grader. The chance of making an error is 0.05. Wow, think of it. There's 5% chance they mark a question wrongly. Multiple choice questions. All right. Okay, so there are 10 questions and marked independently. All right. So what is the probability? No errors are made. No error means all 10 questions are marked correctly. And each question is supposed to mark independently. And that at least one error is made. If there are n questions, what is the probability of making an error? Is p rather than 0.05. So give the expression of these two probabilities in terms of p. All right? So always like this. Define your probability so that you understand what you're doing. So here I define EI to represent that the ith questions, all right, mark wrongly. The error in the marking of the ith questions. All right? So now I have E1 up to E10. What we are asked is to find that there are no error, which means that we are working on, all right, E1 prime, E2 prime, and E10 prime. No error for all these 10 questions. Because marking have errors, these events are independent, therefore this E1 prime, E2 prime, and E10 prime are all independent. So probability of no error in the 10 question translated means probability of E1 prime intersect E2 prime up to E intercept of E10 prime. So it's equal to the product of this one, means 1 minus 0.05. This is 1 minus 0.05. This is also 1 minus 0.05. So altogether you have 10 factors. Each is 1 minus 0.05. So the answer is 0.59. 60%. Wow. Terrible, huh? So no mistake, 60% chance only. Right? So, what is the probability of at least one error? At least one error means 1 error, 2 error, 3 error, 4 error, 5 error, up to 10 errors. Wow. Then what to do? Will you compute probability of only 1 error? How to compute this probability? In terms of the EI, what does it mean? 1 error. What does it mean? It means that E1 intersect the second one, E3 up to E10. This is only the error occur in the first questions. Then union. Wow. E1 complement E2, and then E3 complement, and so on. 10 of them. This is only probability, only describing one error. It can be the first error, error in the first question, or error in the second question, or error in the third question, and so on. And this is only one error. I still have to work out 2 errors, 3 errors. Wow. So don't waste time on this. There's a simple way to do it. No error. The complement of no error means that there's error. And we did not specify what number is it. It can be 1 error, 2 errors, and so on. So in other words, the probability of at least 1 error means 1 minus, because this is the complement event of this. So the chance is 40%. So in other words, there are 40% chance that there will be some error. It can be 1 error, it can be 10 errors. So altogether, an error is 40%. Very high chance. But we don't have such high chance of making errors. We almost have 0 chance of making errors. I cannot say 0, all right? Very, very small chance. The problems here is that the number, think of it, 5% chance of making a mistake in marking one question is very high, right? It should be 0.0000001, very small number. But even very small number, if you multiply 10 times, or what? Okay, if you have a calculator, you work out. Let's say the chance of making an error is like this. All right, 0.001%. But 1 minus it raised to power 10, it may be still quite a big number. Big in the sense maybe okay, I don't know, I have no idea what this number is. But what I'm trying to say is that the chance of making an error in marking one question should be very, very, very small. Okay, so the part C is basically asked, okay, now instead of 5%, let's consider the chance of committing an error is P, represented by P, and then repeat question A and question B. So it will be, replace the 0.05 by P. So it's 1 minus P to power 10. All right? We are able to get this number. What is this number? No, I don't think you have a calculator that can do that. We don't know what P is. So this is the answer. The chance of making no error is 1 minus P to power 10. So similarly, if I extend it to ask, what happens if instead of 10 questions, now it's n questions? All right, so then you just replace this by n. So it's 1 minus P to power n. All right? But I want you to understand that why we replace 10 by n. Because it's not just 10 questions, we change to n questions, so I replace 10 by n. But because we have to multiply this n times, so it's 1 minus P raised to power n. All right, so these are the answers for part A and part B, for n questions and P. Is this the last slide of chapter? Oh, yeah. So we finished one chapter. Any questions? I finished earlier than I thought. All right. Chapter 2, since I just uploaded, I don't think you have it. All right. But I can give you a preview. Just 2 or 3 minutes. Okay. Chapter 1. Okay, let's summarize. In chapter 1, we talk about, all right, how to do counting. In fact, why we want to do counting. Because of, we want to compute the probability based on the number of outcomes. The denominator is the number of possible outcomes. The numerator will be the number of ways that, that you have to fulfill or to satisfy or to meet the requirement. All right? So that is how you get the probability. But make a strong assumption, all the outcomes are equally likely. So therefore, you have to make sure that the outcomes that you're considering are equally likely. So like I buy a 4D ticket, 2 outcomes, winning or losing, they're not equally likely. But the numbers that you specify, they're equally likely. If I want to buy 1, 2, 3, 4, what's the chance that I win? So 1, 2, 3, 4 chance winning is the same as 4, 3, 2, 1. Same as other 4 digits. So that's equally likely outcomes. Okay? Then we talk about probability. So you have to know properties. Okay, before the properties, you must know the axioms of probability. There are 3 basic rules, or we call it axioms. So you have to know that. So the other properties, you also have to know that, but they can derive from the axioms of probabilities. So these properties will help you to compute the probabilities of a given event. Then we also talk about conditional probabilities, and also talk about independent events. We learn about total probability, space rules. All these are applied to events. But chapter 2, we are going to move to talk about something called random variables. And what is random variables? Do you know what is variable? Do you know what is variable? What is a variable? Do you know what is a constant? Is 1 a constant? Is x a variable? If x, all right, always equal to 1, then x is a constant. Don't fool by x. In your algebra, x is always the variable, but x can be a constant. So long as it takes one value all the time, then it is a constant. So variable means that notation takes various value. What's random variable? Random variable is a variable. It must be a variable. Random is to describe the variable. The variable has some certain properties. It takes on values, different values, with different probabilities, or different way of uncertainty, a way to measure the uncertainty. All right? So the simple example is of a random variable. Is a random variable takes the values 0 and 1. So it's not a constant. It takes 2 values, at least 2 values, 0 and 1. But it has a probability of, let's say, half takes 0 and half take 1. That is a simplest random variable. All right. So random variable associated with the probabilities. And then we can talk about expectation and so on. So this one you will watch it in the webcast that I'm going to upload. All right? And how to manipulate the random variable or the properties of random variable. Okay, let me repeat the announcement I just made at the beginning of the lecture. No class next Monday. All right? The 2 to 4 lecture next Monday. All right? Cancelled, I would say. All right? And replace it by webcast. Tutorial, if your tutorial happens to be Monday 4 to 5 and 4 on Tuesday, then go to other tutorials for makeup. All right. Midterm test, likely, okay. It may be, okay, it may be in the morning of 9th of March. All right. So it can be morning, can be afternoon. So leave that open. Thank you.